Download this code from codegive.com, link in the description below. OK, buckle up. This is going to be a deep dive into a specific moment in Templeos history, focusing on a live coding session by Terry A. Davis, the creator of Templeos, on February 12, 2016, where he's tackling a compiler bug. We'll try to reconstruct the context, the bug, his approach to debugging, and ultimately, the fix. This tutorial relies heavily on analysis of archived Templeos source code and the somewhat fragmented records of his live streams. Important caveats ********************************************************************************************************************************************************************************************************************************************************************************************************************************************************************************************* x86-64 operating system written entirely in holyc, a custom language Terry created that's similar to C/C++. The system is highly integrated, with the compiler, kernel, editor, and everything else essentially part of a single monolithic project. This tight integration affects debugging approaches. Terry's style. Terry's coding style was often unconventional and idiosyncratic. Expect code fragments that might not follow typical coding standards. Debugging relied heavily on intuition, immediate feedback loops, compiling and running frequently, and a deep familiarity with his code base. Incomplete information. Exact details from the stream are often lost. We'll infer and reconstruct based on available context. I'll try to indicate where assumptions are made. Focus on the process. This is less about providing a copy/paste solution and more about understanding how Terry approached a debugging problem. Part 1, Setting the Stage, Context and the templeos compiler. Before we can understand the bug fix, we need to appreciate the environment. 1. Templeos' monolithic design. In templeos, everything is compiled directly. There's no separation of compilation and linking phases like in traditional tool chains. The compiler's output is directly loaded and executed. This means compiler bugs can have immediate and far-reaching consequences. 2. holyc and the compiler. Holyc is a C-like language, but with extensions like inline assembly, essential given the low-level nature of templeos. Built-in support for graphics and audio. Metaprogramming features. Direct hardware access. The compiler is responsible for translating holyc code into x86-64 assembly and then assembling and linking that directly into memory for immediate execution. The compiler is a core part of the kernel. 3. Debugging tools, or lack thereof. Templeos lack sophisticated debugging tools in the traditional sense, no GDB-like debugger. Terry primarily used print, statements for output and tracing. Examining memory directly. Disassembly of the compiled code, using templeos' built-in disassembler. Extensive use of the compiler's verbose output to inspect the generated assembly code. Recompiling frequently after small changes to quickly test hypotheses. For the live stream context. Terry often streamed his work, showing him developing and debugging templeos. These streams were often unfiltered and unpredictable. He would jump between different parts of the code base, and the streams had a tendency to cut off randomly. Part 2, Identifying the bug and the code snippet, reconstruction. Based on historical context and reports from those who watched the stream, and later discussions, the bug likely involved code generation for a specific type of struct assignment or member access. It seems to have been related to how the compiler handled the sizes and offsets of struct members. While the exact snippet of code causing the problem is lost, we can create a hypothetical example that captures the essence of the issue. Let's assume the buggy code was something like this. This is an approximation and may not be exactly what Terry was working with. Possible bug scenario asterisk. The compiler might have been incorrectly calculating the offset of the B member within the mystruct structure. In x86-64, structs often have padding inserted to maintain alignment requirements. If the compiler didn't correctly account for this padding, it could lead to writing to the wrong memory location. This could corrupt other data or cause a crash. The offstop macro, which is part of holyc's standard library, should provide the correct offset, but the compiler itself might have been generating incorrect code for it under certain circumstances. Why this is plausible asterisk. Asterisk struct layout complexity asterisk structs with mixed size members, U64, U8, U64, can be tricky for compilers to handle correctly, especially with respect to padding and alignment. Asterisk pointer arithmetic asterisk the line, U8, U64, S plus offstop, mystruct, B, equals 1, involves explicit pointer arithmetic, which can be a source of errors if the offsets are wrong or the compiler makes incorrect assumptions about memory layout. Asterisk GUI connection asterisk templeos was heavily focused on its GUI. Bugs in struct handling could easily manifest as graphics glitches or crashes when drawing GUI elements that rely on specific data layouts. Part 3, Terry's debugging approach, inferred. Given Terry's usual methods, here's a likely reconstruction of his debugging process. 1. Reproducing the crash or error asterisk. The first step would be to reliably reproduce the crash or unexpected behavior. This might involve running a specific program or GUI element that triggered the bug. He would have likely made small changes to the code to isolate the issue. 2. Adding print statements asterisk. Terry would have strategically inserted print statements to inspect the values of relevant variables and memory locations. For example, these print statements would reveal asterisk the actual address of the mystruct instance, asterisk the offset calculated by offstop, asterisk the value of s-b before and after the assignment, to see if the write was happening as expected, asterisk potentially the value of adjacent memory locations to detect corruption. 3. Examining compiler output, verbose mode. Terry would likely have compiled the code with a verbose flag, if the compiler had one, or perhaps by modifying the compiler itself to output more information. This would show the generated assembly code for the drawMyStruct function, especially the parts related to the pointer arithmetic and memory access. He would then try to understand if the assembly instructions were correctly implementing the intended logic. For example, he'd look at the load effective address instruction used for calculating offsets. 4. Disassembly asterisk. If the verbose output wasn't clear enough, Terry might have used templeos as built-in disassembler to examine the compiled code in more detail. This would allow him to see the raw assembly instructions and understand exactly how the compiler was translating the holyc code. 5. Modifying the compiler, likely given that this was a compiler bug, Terry almost certainly would have had to modify the compiler's source code itself to fix it. He would have traced the code generation process for struct member access, looking for the source of the incorrect offset calculation. Part 4, Possible bug fix, hypothetical. Without knowing the exact cause of the bug, we can only speculate about the fix. Here are a few possibilities. 1. Padding calculation error asterisk. The most likely scenario is that the compiler wasn't correctly calculating the padding required for struct members. The fix would involve modifying the code that determines struct layout to accurately account for alignment requirements. This might involve changes to the offstop macro implementation or how the compiler represents struct types internally. 2. Instruction selection error asterisk. The compiler might have been selecting the wrong x86-64 instructions for accessing struct members. For example, it might have been using an instruction that assumed a different memory layout. The fix would involve modifying the compiler's instruction selection logic to choose the correct instructions based on the struct's definition. 3. Type conversion issue *. There might have been a problem with how the compiler was handling type conversions during pointer arithmetic. The explicit cast2, U8*, could have exposed a bug if the compiler was making incorrect assumptions about the size or alignment of the resulting pointer. The fix might involve tightening up the type checking or modifying the code generation for type conversions. Example of a possible compiler modification, illustrative. Let's imagine that the issue was in a function within the compiler that calculates struct member offsets. This function might look something like this. Again, this is a highly simplified and speculative example. The original code might have been missing the padding calculation, as indicated in the comment. The fix would involve adding code to account for the padding required to align the next member. This is a highly simplified example, but it illustrates the kind of change that might have been necessary. Part 5, the templeos way, iterative and integrated. The key takeaway is that Terry's debugging was an iterative and highly integrated process. He would make small changes to the compiler. Recompile templeos immediately. Run the affected code to see if the bug was fixed. Repeat until the bug was resolved. This fast feedback loop, combined with his deep understanding of the entire system, allowed him to diagnose and fix complex compiler bugs. Code example summary, putting it all together. Key takeaways about debugging in templeos and Terry's style *. Embrace the integrated environment *. Understand that in templeos, the compiler, kernel, and everything else are deeply intertwined. Debugging often requires jumping between different parts of the system. Use print, liberally *. Don't be afraid to use print statements to inspect variables and memory locations. This is often the most effective way to understand what's going on. Examine compiler output *. Learn how to generate verbose compiler output and how to disassemble code. This will give you valuable insights into how the compiler is translating your code. Be prepared to modify the compiler *. If you're dealing with compiler bugs, you'll likely need to modify the compiler's source code itself. Iterate quickly *. Make small changes, recompile, and test frequently. This will help you isolate the bug and verify your fix. Intuition and experience *. Terry relied heavily on his intuition and experience. The more familiar you are with the templeos code base, the better you'll be able to debug it. This tutorial has been a reconstruction based on limited information. The exact bug and fix from the February 12, 2016 livestream may be different. However, the principles and techniques outlined here should provide a valuable insight into Terry A. Davis's approach to debugging templeos. Good luck debugging.